Alright, welcome back everybody. In this video we're going to talk about polar to Cartesian conversions, how we can convert from a polar equation to a Cartesian equation. First things first, I'm going to explain where all these relationships come from, and I'm going to pick the right thing. Let's try this again. There we go. So what we have is we have a unit circle, and I missed by a little bit in my drawing here. Looks better. We have a unit circle overlaid over the coordinate plane. And for a particular angle of theta, if I draw in any angle here, theta, all of these relationships come from this particular drawing. We have the angle theta with radius r. The x-coordinate at that point is this distance right here, which is r times the cosine of theta. The y-coordinate of this point is r times the sine of theta. Okay, because this is a right triangle, x squared plus y squared equals r squared. And since this is my angle theta, the tangent of the angle theta is equal to the opposite over the adjacent, so it's equal to y over x. That's where all four of these relationships that we have here come from. And these are the common relationships that we use to convert equations from polar form into Cartesian form. Alright, so let's go ahead and do that. We'll look here in example 1. We're going to convert these polar equations into their Cartesian equivalent. The first one is pretty simple. We've got r cosine of theta equals 2. We know that r cosine of theta is equivalent to x, and so we can rewrite this polar equation as the Cartesian equation x equals 2. In that case, Cartesian equation looks a lot less complicated than the polar equation. Well, not a lot less, but looks less complicated than the polar equation. Alright, let's look at part B. R squared cosine of theta sine of theta equals 4. What I'm going to do is I'm going to regroup these. I'm going to turn that into r cosine of theta times r sine of theta equals 4. And then r cosine of theta is equal to x. R sine of theta is equal to y. And so this is the equation xy equals 4. Again, the Cartesian equation in this case looks better than the polar equation. Alright, let's see what we've got here. R squared cosine squared of theta minus r squared sine squared of theta equals 1. So that's just the quantity r cosine of theta, quantity squared, minus the quantity r sine of theta, quantity squared, equals 1. R cosine of theta is equal to x. R sine of theta is equal to y. And so this is the equation x squared minus y squared equals 1. So far, all of the Cartesian equations have been significantly more simple than the polar form. That's not always the case. Alright, let's see what we've got here. R equals 1 plus 2r cosine of theta. Let's see. So I can replace r with the square root of x squared plus y squared, because x squared plus y squared equals r squared. And I can replace r cosine of theta with an x. And now in order to get the best form of this equation, I'm going to square both sides of this equation. That gives me x squared plus y squared equals the quantity 1 plus 2x quantity squared. And so we've got x squared plus y squared equals 1 plus 4x plus 4x squared. And so this equation ends up being 0 equals 3x squared plus 4x plus 1 minus y squared. Or y squared equals 3x squared plus 4x plus 1. Either one of those I think is good. Alright. Now here, for the first time, it looks like the Cartesian expression of this equation is a little bit more complicated than the polar form. And that happens sometimes. Alright. On to part E. R equals 1 minus the cosine of theta. Now, I can't replace this cosine of theta with anything. So what I'd like to do is I'd like to multiply it by r, because that would give me r cosine of theta, which we know we can replace with an x. So I'm going to multiply this whole equation by r. That's going to give me r squared is equal to r minus r cosine of theta, which is now making replacements. R squared is x squared plus y squared, and r is the square root of x squared plus y squared, and r cosine of theta is x. Simplifying this and getting rid of the radical, I'm going to add x to both sides. And then I'm going to square both sides of this equation. So I have x squared plus y squared plus x, quantity squared, equals x squared plus y squared. And now I need to square this out. So let's see, that gives me x to the fourth plus x squared y squared plus x to the third plus x squared y squared plus y to the fourth plus xy squared plus x to the third plus xy squared plus x squared equals x squared plus y squared. Great googly moogly. Let's see, things that I can... Sorry about that. Another phone call interrupting me. So let's see, what we want to do here is we want to combine any like terms that we have, and so I'm going to look for terms that I can combine. I've got some x squared y squareds that are like there. I've got some xy squareds that are like there. I've got some x to the thirds that are like, and I've got some x squareds that are like. And so we're going to combine all of those. So let's see, I've got x to the fourth plus 2x squared y squared, that takes care of the yellows, plus 2x to the third, that takes care of the greens, plus y to the fourth plus 2xy squared, and got a minus y squared equals 0. And I can reorder these terms if I want to so that they're, descending degree. I could write this as x to the fourth plus 2x squared y squared plus y to the fourth plus 2x to the third plus 2xy squared minus y squared equals 0. But you'll notice that in this case, the Cartesian equation, if you compare it to the polar equation that we started with, the polar equation is much nicer. Alright? It says here, one thing you should have noticed, there are equations that are simpler to write in polar form than Cartesian form, and other ones that are simpler to write in Cartesian form than polar form. If nothing else, this should show you the necessity of having both of these notational systems available to us in order to be able to best write an equation that describes whatever situation we encounter. It's nice to have multiple tools in order to write these equations for simplicity's sake. Alright, we're going to stop there with this video. We'll come back next time and look at examples 2 and 3. See you guys then. Have a great rest of your day.